Hey there. Hope you guys are doing well. So here I am in my office, going to try to give you a lecture this way. Let's see how it goes. So we're going to be talking about relativistic dynamics. How do we generalize Newton's laws to take into account special relativity? All right. And the basic idea is to try and translate everything so that it has a natural transformation law under the change of reference frame. So we'll turn everything into either a scalar, something that's the same in every reference frame, or a 4-vector. And later we'll get to some tensors. Okay? So we have a space-time diagram. Okay? And suppose we have some particle whose motion we're trying to describe. Okay? So this particle has a world line. Okay? And this world line tells us the history of this particle. Okay? Now, in normal Newtonian dynamics, we keep track of when the particle is by some time coordinate. But in special relativity, the time coordinate depends on the reference frame. So a more invariant way to keep track of where the particle is, or when it is on its world line, is in terms of its proper time, tau, right? So tau is the proper time. That's the time is measured by a clock that is moving with the particle, okay? So let's consider two nearby events, okay, on the world line. So this represents the particle at two different instants of time, or two different proper times. So we have proper time tau and proper time tau plus delta tau, all right? And what is delta tau? Delta tau is equal to the square root of delta t squared minus delta r, the position vector squared, over c squared, okay? Now, I am going to set c equal to 1. C's in formulas like this, they clutter everything up, they make things less clear, and I'll get them wrong every time, so I don't want that to be a distraction. So I'm just going to set c equal to 1, okay, from now on, all right? Okay, so, and we can always restore the factors of c. Sometimes I'll restore them to make a point about the non-relativistic limit and so on, okay? But anyway, all right. Now, since these 2 points are close together, I can approximate delta r, okay, as being the velocity, the instantaneous velocity times the change in time, okay? Now, we're going to follow the notation of Griffiths, even though I don't like it very much, but we'll follow it, so you will agree with what the book says. And so we'll denote the ordinary 3 velocity by u. So this is u delta t, okay? And so if we just plug this into here, what we get is that delta tau is equal to delta t, okay, times the square root of 1 minus u squared. I'll just write u squared. There we go. Okay? All right? So now the idea is now we can take the infinitesimal limit, right? We just take delta t to 0 and delta tau to 0. We can write this as d tau is equal to dt 1 minus u squared. Okay? All right? So now, the way to look at this formula is that d tau is the change in the proper time. That is the same in every reference frame, right? Whereas dt depends on the reference frame, and u, the ordinary 3 velocity, also depends on the reference frame. So this formula relates things that we're used to that are defined in terms of a reference frame in terms of a more enlightened special relativity quantity that is independent of the reference frame. Okay? All right? So, for example, just to emphasize this, u, okay, the ordinary 3 vector would be dx, or let's call it dr, dt. That is the ordinary 3 velocity, right? But both r and t change when you change reference frames and so on. Now what we want to do is we want to define a 4-vector quantity that encodes the velocity of the particle. And we do that, we call this thing eta mu. Again, this is a terrible Griffith notation, but I'll follow it, okay? So eta mu is dx mu d tau, Okay? So what we're doing here is we're taking the 4-vector, okay, position of the particle, right? So x mu is a 4-vector, and we're differentiating it with respect to, or dividing it by the change in proper time, okay? And that will, this quantity, therefore, is by definition a 4-vector, okay? It transforms as a 4-vector under the change of Lorentz frame, okay? All right. So let's work out the relationship between this 4-vector and the quantities that we're used to, like the ordinary 3 velocity. Okay, so to do that, we just look at the components. So let's first of all look at the spatial components, eta vector. Okay, what are the vector components of eta? Well, we see that that's just equal to dr d tau. Okay, right? From because the spatial components of x mu are just the position vector. Okay, and d tau we can relate to dt by this formula right here. So this is 1 minus 1 over square root 1 minus u squared d by dt r. Okay, and that in turn is just u over square root 1 minus u squared. Okay, so we see that the spatial components of eta are proportional to the velocity, but there's this normalization factor. And similarly, eta 0 is just dt d tau. Okay, remember there's no c is equal to 1, so there's no ct or anything like this. I don't need to worry about that. Okay, and this thing is just 1 over square root 1 minus u squared. Okay. So we see that both the spatial components and the time component of eta are given by, in terms of the 3 velocity, by these equations right here. Okay? Okay. How do we generalize Newton's laws to take into account special relativity? All right. And the basic idea is to try and translate everything so that it has a natural transformation law under the change of reference frame. So we'll turn everything into either a scalar, something that's the same in every reference frame, or a 4-vector. And later we'll get to some tensors. Okay? So we have a space-time diagram. Okay? And suppose we have some particle whose motion we're trying to describe. Okay, so this particle has a world line. Okay, and this world line tells us the history of this particle. Okay, now in normal Newtonian dynamics, we keep track of what when the particle is by some time coordinate. But in special relativity, the time coordinate depends on the reference frame. So a more invariant way to keep track of where the particle is, or when it is on its world line, is in terms of its proper time, tau, right? So tau is the proper time. That's the time is measured by a clock that is moving with the the particle, okay? So let's consider 2 nearby events, okay, on the world line. So this represents the particle at 2 different instants of time, or 2 different proper times. So we have proper time tau and proper time tau plus delta tau. All right. And what is delta tau? Delta tau is equal to the square root of delta t squared minus delta r, the position vector squared, over c squared. Okay. Now I am going to set c equal to 1. C's and formulas like this, they clutter everything up, they make things less clear, and I'll get them wrong every time, so I don't want that to be a distraction. So I'm just going to set c equal to 1, okay, from now on, all right? Okay, so, and we can always restore the factors of c. Sometimes I'll restore them to make a point about the non-relativistic limit and so on, okay? But anyway, All right, now since these 2 points are close together, I can approximate delta r, okay, as being the velocity, the instantaneous velocity times the change in time. Okay. Now we're going to follow the notation of Griffith's, even though I don't like it very much, but we'll follow it, so you will agree with what the book says. And so we'll denote the ordinary 3 velocity by u. So this is u delta t. Okay. And so if we just plug this into here, what we get is that delta tau is equal to delta t, okay, times the square root of 1 minus u squared. I'll just write u squared. There we go. Okay. All right. So now the idea is now we can take the infinitesimal limit, right? We just take delta t to 0 and delta tau to 0. We can write this as d tau is equal to dt 1 minus u squared. Okay? All right? So now the way to look at this formula is that d tau is the change in the proper time. That is the same in every reference frame, right? Whereas dt depends on the reference frame, and u, the ordinary 3 velocity, also depends on the reference frame. So this formula relates things that we're used to that are defined in terms of a reference frame in terms of a more enlightened special relativity quantity that is independent of the reference frame. Okay? All right. So, for example, just to emphasize this, u, okay, the ordinary 3 vector would be dx, or let's call it dr, dt. That is the ordinary 3 velocity, right? But both r and t change when you change reference frames and so on. Now what we want to do is we want to define a 4-vector quantity that encodes the velocity of the particle. And we do that, we call this thing eta mu. Again, this is a terrible Griffith notation, but I'll follow it, okay? So eta mu is dx mu d tau, okay? So what we're doing here is we're taking the 4-vector, okay, position of the particle, right? So x mu is a 4-vector, and we're differentiating it with respect to, or dividing it by the change in proper time, okay? And that will, this quantity, therefore, is by definition a 4-vector, okay? It transforms as a 4-vector under the change of Lorentz frame, okay? All right. So let's work out the relationship between this 4-vector and the quantities that we're used to, like the ordinary 3 velocity, okay? So to do that, we just look at the components. So let's first of all look at the spatial components, eta vector, okay? What are the vector components of eta? Well, we see that that's just equal to dr d tau, okay, right? From, because the spatial components of x mu are just the position vector, okay? And d tau we can relate to dt by this formula right here. So this is 1 minus 1 over square root 1 minus u squared d by dt r, okay? And that in turn is just u over square root 1 minus u squared, okay? So we see that the spatial components of eta are proportional to the velocity, but there's this normalization factor. And similarly, eta 0 is just dt d tau. Okay, remember there's no c is equal to 1, so there's no ct or anything like this. I don't need to worry about that. Okay, and this thing is just 1 over square root 1 minus u squared. Okay, so we see that both the spatial components and the time component of eta are given by, in terms of the 3 velocity, by these equations right here. Okay? Okay. Okay. Let's use this to work out the rule for addition of velocities. Okay? So let's look at a situation where we have 2 Lorentz frames. Okay, we have O and O prime, okay? And O prime is moving with speed v relative to O. So the notation that Griffiths uses that we'll also use is that v is always going to be a velocity that transforms between one reference frame and the other. Okay? And now the quantity that we want to transform is the vector u, right, where u is dr dt. It is the velocity, the 3 velocity of some particle as measured in reference frame O. Okay? And what we want to know is what is u prime, okay? And u prime would be dr prime dt prime, okay? Now, we can work this out by using the Lorentz transformations, okay, on r and t, but we can also work it out here in a simple way using this 4-vector eta, and that's what I'm going to show you now, okay? Okay, so we do the following. We just use the fact that this eta transforms as a 4-vector, and so that tells us 2 things, right? That tells us that eta prime, the vector component of this, is gamma eta minus v eta 0, okay? So this is the Lorentz transformation for a vector, the spatial components of a 4-vector. Okay, and so using this, and gamma is equal to 1 over square root 1 minus v squared. Okay, v is the transformation velocity between the reference frames. And so if we plug in here what eta and eta 0 are, these formulas are valid in any reference frame with appropriate primes. And so for eta prime, what we get is u prime divided by square root 1 minus u squared, okay? And that's equal to gamma, which is 1 minus v squared, 1 over square root 1 minus v squared. And then both of these guys have a factor of square root 1 minus u squared, which we'll factor out, okay? And then what's left inside is just u minus v, okay? All right? So this is just plugging in. Here is the transformation rule for the spatial component of a 4-vector, and then we just plugged in what we found for those in both the primed and the unprimed frame. Okay? And similarly, we have that eta prime 0 is equal to gamma eta 0 minus v dot eta. Okay? So this is how the 0 component of a 4-vector transforms. Okay? And again, plugging in these equations down here, what do I get? Here I just get 1 over square root 1 minus u prime squared. And I'm sorry, I made a mistake here. This should be a u prime squared, okay? Because everything here on the left side here is primed. And it's the same thing here. This eta prime 0 is written in terms of u prime. Okay? And then this is equal to 1 over square root 1 minus v squared. That's this gamma factor. Then each one of these factors has a 1 minus u squared. Okay? And then what we have left inside is just 1 minus u dot v. Okay? All right? So we obtained these 2 equations right here. Okay? We obtained these 2 equations right here. Okay? Just from transforming eta as a 4-vector. Okay. Now what we can see is we can use the second formula to rewrite this 1 over square root 1 minus u prime squared in the first formula. Okay. So we'll plug this formula into that. Okay. And then what do we get? Okay. Well, on the left side we get u prime vector, and we have these 2 square roots, 1 minus u squared 1 minus v squared from the right-hand side here. And we have 1 minus u dot v, okay? And then on the right side, we have these same 2 square roots, 1 minus v squared, 1 minus u squared in the denominator, okay? And then we simply have u minus v, okay? And then a lot of the nasty bits cancel out. 1 minus u squared cancels against 1 minus u squared. 1 minus v squared cancels against 1 minus v squared. As I always say, when you're a nerd, you get very happy and excited when lots of things cancel. And so then we get a formula, I'll write it over here. U prime is then equal to u minus v, okay, divided by 1 minus u dot v, a relatively simple formula, okay? All right, and this is indeed the correct formula for the transformation of velocity. Okay, that you could have gotten by laboriously doing the Lorentz transformations, but we see it follows in a fairly simple way from the fact that eta is a 4 vector. Okay. Now let me just make a little comment about the speed of light. I've set it equal to 1, but it's very easy to restore it just using dimensional analysis. So for example, u prime has dimensions of velocity, and so the u and the v in the numerator here have the right units. But down in the denominator, I have 1 minus square of the velocity. So I can easily restore the units by putting in factors of c, and I'll put in just a 1 over c squared here. Okay, so I can always do this. It always kind of is that easy. And I do this, what I can see is that when c goes to infinity, right, this correction in the denominator, I get 1 minus something that goes like 1 over c squared. So when c goes to infinity in the non-relativistic limit, this denominator just goes to 1, and I just get the famous non-relativistic answer that the velocities just add, or rather subtract. If you look at this picture, you see that that's actually the correct way, because if O is moving with speed v relative to O prime, then the velocity measured in this frame, you subtract v in the non-relativistic limit. Okay? So sorry for the jarring transition. I think this will work better. I'm still figuring this out, so please bear with me. All right, we now want to talk about acceleration. So just as we were able to describe the velocity of a particle in terms of it's kind of jarring. I guess that makes sense. I guess I don't want it to be a mirror. All right. Okay, folks, sorry for the rough transition. I'm still working on getting the best technical arrangement, so please bear with me. All right, now we want to talk about acceleration. We saw how to describe the velocity of a particle in terms of a 4 vector, the 4 velocity, and now we want to describe the acceleration in terms of a 4 vector, the 4 acceleration. And you can probably already guess what the definition will be. So we start with the 4 velocity, eta mu, and then we differentiate that with respect to the proper time, okay? And that is guaranteed to be a 4 vector, which we call the 4 acceleration, okay? So that is guaranteed to be a 4 vector, okay? Now, just as we found that the 4 velocity did not have 4 independent components, it was completely determined by the 3 velocity in any given reference frame, the ordinary 3 velocity. We want to do the same thing for the 4 acceleration. Now, the relationship that told us that the 4 velocity didn't have 4 independent components was that eta mu was equal to -1, right? The Lorentz invariant square of this 4 vector was equal to -1. So now we're going to use this relation to find a constraint on alpha mu. And the way we're going to do that is just differentiate this with respect to proper time. So if we differentiate this with respect to proper time, because this is -1, we just get 0. So we have 0 is equal to d by d tau of eta mu. Okay? And now we just write this out, okay, using the chain rule, and we have d eta upper mu d tau eta lower mu plus eta upper mu d eta lower mu d tau. Okay, so we just get these two terms. These two terms look very similar, and in fact, they're just equal to each other. The reason is that for any 4 vector, we have a mu b lower mu is equal to a lower mu b upper mu, right? This is true for any Lorentz invariant contraction of these indices, because lowering one index and raising the other just changes the sign of that vector for the time component leaves the other one alone. So for both of these, this is equal to A0, B0, sorry, minus A0, B0 plus A vector dot B vector, right? So it doesn't matter whether we raise and lower the indices. And so these two terms are actually equal to each other. Since the sum of them are 0, each one is 0. And this right here, d eta mu d tau, by definition, is just what we called alpha mu, right? The 4 acceleration. So we learn that eta lower mu alpha upper mu is equal to 0. Okay? So just like the 4 velocity, the 4 acceleration also satisfies a Lorentz invariant constraint like this. Okay? Now this constraint means that the 4 components of the alpha mu are not independent. And to see what that relationship is, let's just plug into that relation. Let's just plug in what eta is. Okay? So that relationship right there tells us that eta 0 is equal to minus eta 0 alpha 0 plus eta vector dot alpha vector. Okay? And plugging in what this is, eta 0 and eta vector are both proportional to 1 over square root 1 minus u squared. And then what we have left over here is just 1, so we have minus alpha 0. And here we have a u. Okay? And since this is 0 and this is never 0, we see that alpha 0 is just equal to u dot alpha vector. Okay? So we see very explicitly that the time component of alpha is determined completely by the spatial components and the 3 velocity. Okay? All right. Okay, so now let's stop. Okay, now we want to determine the relationship between alpha vector and the ordinary acceleration. The ordinary acceleration A is just given by du dt, right? That's the ordinary acceleration. And we want to find the relationship between this and the alpha vector. And to do that, we just use the definition of the alpha vector, namely that it's d by d tau of the eta vector, right? And now we can just write d by d tau in terms of d by dt using the chain rule. We have 1 minus u squared d by dt. And then we write out what eta vector is. It's u square root 1 minus u squared. Okay? And so now we just need to differentiate this, right? So d by dt hits this u and gives us the acceleration. It also hits this u magnitude, and so we have to do some chain rule and do a little bit of simplification. And I'm not going to do that in step by step, but what you get after a few steps of algebra, I'll write out what you get. You get a 1 over 1 minus u squared, open parentheses, a plus a dot u divided by 1 minus u squared times u. Okay? So this is what you get for alpha. Okay? So as promised, the alpha vector is determined by the ordinary acceleration and the ordinary velocity vector. Okay? And we can similarly then use this relationship here to write out what alpha 0 is. And after a small amount of simplification, we'll get alpha 0 is equal to u, let's say, a dot u divided by 1 minus u squared all squared. Okay? So in any given reference frame, we have figured out what the components of the 4 acceleration are. So let's use this to find out what kind of 4 vector is alpha mu. Is it time-like, space-like, null? What is it? Okay? And the way we did that for the 4 velocity was we found the Lorentz invariant square of the 4 vector. So we can imagine doing that here as well. We can try to ask, what is alpha mu alpha mu? What is this object? Okay. Now, we could use these expressions and try to simplify it in a general frame, but that gets rather messy. So a very useful trick in this case and in many other cases is to go to the instantaneous rest frame of the particle. Now, the instantaneous rest frame is not the frame that's moving with the particle. So we imagine we have a particle that's moving in some, in general, complicated way. It's not constant velocity or constant acceleration or anything. It's just a complicated motion. But we can choose a reference frame, an inertial reference frame, so that at a given instant in the motion, the particle is instantaneously at rest. Okay. So that in that frame, right, at that instant, u is equal to 0. Of course, at a later time, u will not be 0. But for a short amount of time around the place where u is 0, the particle will be non-relativistic. So this is a very useful tool to make the connection between the to generalize non-relativistic mechanics to relativistic mechanics. Okay. But here, we'll just use it to figure out what kind of 4-vector alpha is. And so we see that we can go to a reference frame where u is instantaneously 0. And when we do that, right, if u goes to 0, it's very easy to see that this almost everything goes away here. This term completely goes away. This denominator is just 1. And so the alpha vector just becomes a, the ordinary acceleration. And the alpha 0 vector just goes to 0. Okay? So in the instantaneous rest frame, the alpha vector is just equal to the ordinary acceleration, and the spatial components of the 4 velocity are just the ordinary. The spatial components of the 4 acceleration are just the ordinary acceleration, and the time component vanishes. Okay? So in particular, that tells us that the square, the Lorentz invariant square, which is just minus alpha 0 squared minus alpha vector squared, sorry, plus alpha vector squared. In the instantaneous rest frame, this just becomes plus a squared, right? It just becomes the square of the ordinary 3 velocity. And so in particular, but the sign of this thing has to be the same in every reference frame. So this is always positive in every reference frame. And so what we learn is that the 4 acceleration is always a space-like 4 vector. Okay, it's always space-like. And in the instantaneous rest frame, its spatial components are just the ordinary acceleration. All right, let's use this to talk about the simplest kind of motion beyond constant velocity, which would be constant acceleration. Now, I put that in quotes because it's not immediately obvious what should be constant in constant acceleration. So the most natural thing is, if you took it literally, is to say that A, the ordinary 3 acceleration, is constant. Okay? Is that what we mean? I'll put a question mark there. It can't be, because if the acceleration, for example, was in the x direction, then for the simplest initial conditions, this would tell us that x is equal to 1/2 a t squared. So, and the velocity just increases linearly with time. And so after some amount of time, the velocity would get faster than the speed of light. That can't possibly be what happens to any particle. Okay, so this is absolutely not correct. The 3 velocity is not what is constant. What I claim is the right thing to describe what we would mean by constant acceleration is that the square of the 4 acceleration, alpha mu, that this thing instead is a constant. Okay, all right. Now, why is that the correct physical notion of constant acceleration? Well, the key idea is to think about the instantaneous rest frame of the particle. Okay, so what we just saw is that in the instantaneous rest frame of the particle, then this quantity right here is just equal to the square of the acceleration. And I'll put a little knot right here because a0 is the ordinary acceleration in the instantaneous rest frame, so we'll call that the proper acceleration. Okay? All right. Now, the idea is that this is what is the frame invariant, the Lorentz frame invariant measure of how fast a particle is accelerating. So, for example, suppose that we were in a rocket ship, okay, and the rocket ship was moving with alpha mu equals constant equal to this proper acceleration, and suppose that that acceleration was 9.8 meters per second squared. Then, at every instant, we could talk about a frame where an inertial frame where at that instant we are at rest inside the rocket ship, right? But in that frame, the rocket ship is accelerating at 9.8 meters per second squared, say, upward. So we would feel a fake gravity of 9.8 meters per second squared downward. And that would be true at every moment in time. So we would be in this rocket ship and it would be constantly accelerating, and we would always feel pushed to the floor by the same amount of effective gravity force. Okay? So I claim that this is the physically correct notion of constant acceleration. And later on, we will see that indeed, for example, if we put a charged particle into a constant electric field, this is the kind of motion that it has. So it is also the kind of motion that generalizes constant acceleration motion in that case. Okay? So let's run with this. Let's assume that we're interested in this kind of motion right here. And now what we want to find out is, what does the trajectory of a particle look like that has this kind of motion? Okay? And to do that, what we want to do is we want to evaluate, right, this quantity right here, okay, in terms of the 3 velocity, okay? And we're going to do that for the simplest case where everything is in the x direction, okay? The motion is in the x, the particle is moving along the x-axis, and so the velocity and acceleration, etc., has only x components, okay? And so what we do is to evaluate this, this is minus alpha 0 squared plus alpha vector squared, okay? And we gave expressions for that just now, and we now will plug in where everything is going in the same direction and do a little bit of simplification. And then what you find is that this is equal to a sub x squared times 1 minus u sub x cubed. So u sub x squared all cubed. Okay, so you get a relatively simple expression for the square of this, the 4 acceleration. And that should be equal to a0 squared, right? The proper acceleration squared. Okay? So one of the things that you see here from this expression already, this is constant, right? But as time goes on, we expect the particle to move faster and faster. And as it does, this number right here becomes a smaller number in the numerator, right? And so what it means is that if we put it over here, the acceleration is actually getting smaller the faster the particle is moving. Okay? And we'll find out that this is enough to prevent the particle from going faster than light. Okay? All right. So let's to find out what the motion of this particle is, we can just solve for the ordinary acceleration, right? And the ordinary acceleration is dux dt, right? That is the ordinary acceleration, and that is going to be equal to a0, okay, times 1 minus u sub x squared to the 3/2, okay? So that is just what we get by putting this over here and taking the square root, okay? And this can be viewed as a differential equation for for ux. We have dux, it's separable, so we can write this as 1 minus ux squared to the 3/2 is equal to a0 dt. Okay, so this is a separable differential equation for ux. okay? And we can integrate this to find that ux over square root of 1 minus ux squared is equal to a0t plus a constant, okay? That is the most general thing that we get by integrating both sides of this equation right here, okay? Now, we're just going to find the simplest possible solution, okay? So notice that the fact that we can add a constant here just corresponds to our freedom to choose the origin of time, okay? So we're just going to set this constant to 0, and we see what that means is that means that use of x at t equals 0 is equal to 0, right? So we're saying that t equals 0 is the time where the particle is at rest in whatever frame we're talking about. Okay? All right. Okay, so now we've found what the acceleration is as a function of time, or at least we've determined it here in this equation right here. Okay? And in fact, we can solve that equation. So we solve that equation, and we get u sub x is equal to a0t, okay, times square root 1 plus a0 squared t squared. Okay? So that's what we have so far. All right. Now we want to go from the velocity. We've determined the velocity is a function of time. Now we want to determine the position as a function of time. So we do this by writing, so u sub x is just dx dt, right? And so dx is equal to a0t square root 1 plus a0 squared t squared dt, okay? And now we can integrate both sides of that equation, okay? And we just get x is equal to 1 over a0, okay? Square root 1 plus a0 squared t squared plus, again, we have a constant of integration, all right? And this time, the constant of integration corresponds to shifting x, right? We can shift x and choose this constant of integration as we want. So we'll, again, just to get the simplest solution, we will choose this constant of integration to be 0. So that's telling us that x at t equal to 0 is equal to 1 over a naught. Okay, that's kind of a random choice, but that's fine, okay? That's just a choice of the origin. And then we can work out, now we can solve this equation easily and find out that what it tells us is that x squared minus t squared is equal to 1 over a naught squared. Okay? So that is the trajectory that we get when we have this form of constant acceleration. What does this trajectory look like in a space-time diagram? So if we have time and space like this, right, then this is actually a hyperboloid. So here are our light cones. And let's assume that we're interested in the solution with x larger than 0. So the particle is in the positive x-axis. Then this trajectory looks like this, okay? And as t goes to plus infinity, it approaches the speed of light in the positive x direction, and as t goes to minus infinity, this is approaching the speed of light in the negative x direction. So for example, you can see that, for example, from this expression right here, okay? So as t goes to plus infinity, this denominator right here, as t goes to plus infinity, this term down here, let's look at this thing right here. So as t goes to plus or minus infinity, right, then this term in the denominator dominates, and we have a0t divided by, and this is the square root of a0t, which is always the absolute magnitude of a0t, right, for large t, and this indeed goes to plus or minus 1, right? So as t goes to plus infinity, the velocity is going to 1, namely the speed of light. As t goes to minus infinity, it's going to minus 1, namely the speed of light in the opposite direction, okay? And so this is the kind of motion that you already studied in one of your homework problems, okay? And now we understand the sense in which it corresponds to constant acceleration.